Hello there. In this part of the course, we are going to understand what time series forecasting is and how to implement it into Python. In this lecture, we will briefly explain the idea of forecasting before using Python to make predictions based on a simple autoregressive model. We'll also compare the results with the actual values for each period. Okay, for starters, when we're forecasting, we're basically trying to predict the future. This word should sound familiar, since we often hear about it on the news, be it in relation to the weather, politics, or another topic. Colloquially, we use predict and forecast interchangeably. However, there's a very intricate distinction between the two, which we'll explain later in the course. As you already know, in time series, we expect patterns to persist as we progress through time. Therefore, we follow a simple structure. Find the pattern, predict the future. Of course, finding the pattern is just a fancy way of saying selecting the correct model. So we're already halfway done. All that's left is making the predictions. So let's jump right to it. We start by loading up the template file we provided for this section. Just like the AutoArima one, it contains the code for scraping the data, creating returns, normalizing them, and then separating the training and testing sets. If any of this looks unfamiliar, please refer to the lecture on updating the dataset in the Creating a Time Series Object section. Right. Before we proceed, make sure you run the code so we can have the data available and ready. The first bit of coding we need to do ourselves involves fitting the model. As we mentioned earlier, we're going to start off with a simple autoregressive model and see how predictions evolve over time. And as before, we can name the variable model AR. To ensure we'll need to make minimal changes in the future, let's use the ARIMA method here instead of the ARMA. We want to stay consistent with the rest of the course, so we're going to use footsie values once again. Lastly, we must set the order to 1, 0, 0, since this is the ARIMA equivalent of the AR1. Of course, we also need to store the fitted results before moving on. Fantastic. Next up, we must specify the time interval we're predicting. It could be a day, a week, or whatever period we feel like making it. Of course, the starting date of the forecasted period is basically the first one we don't have values for. In other words, we're looking for the first day after the end of the training set. We call the tail method, and whatever the last shown date is, we select the first business day following it. For convenience, we will store the date in a variable called startDate. Similarly, we can store the last date of our interval in a variable called endDate. As explained earlier, we can set it equal to any day from the 14th of August 2014 onwards. The longer the period is, the harder it is to closely see how the data moves between dates. So let's go with some mid-range value. We'll start with the 1st of January 2015, but you can alter it at any time. Great! After setting everything up, we can finally make a forecast using the predict method. We do this by setting dfpred equal to the results variable .predict. Inside the parenthesis, we set the start and end arguments equal to the starting and ending dates we defined earlier, and we're good to go. All right, to get an idea of what our predictions look like, let's graph them using the plot method. We can also specify the color of the plotted time series by defining the argument of the same name. Conventionally, we prefer using blue for actual values and red for predicted ones, so let's indicate that. By all means, remember to define the appropriate figure size and set a title. A name like predictions seems fitting. After adding the plt show command, we can run the cell. We see a constantly decreasing line, which isn't at all realistic. In practice, we don't expect prices to be constantly declining. That would mean that the price today is as high as it's ever going to be, and the price tomorrow will always be lower. If that was the case, sellers would always want to get rid of their investments, but buyers would have an incentive to hold off before they purchase. Then everybody would be trying to sell, but nobody would be willing to buy. The issue here comes from our model of choice. Because we're using a simple AR model, the predictions are only based on the constant and the prices from the previous period. Thus, we get into this constant pattern of creating a curve, where every new value is just a fraction of the previous one put on top of the constant term. We can see the curve better if we zoom out a little bit. To achieve that, just expand the prediction interval and then plot the results one more time. The new plot shows the curve much better than the previous one, so we can verify this unrealistic decline. Now you understand why the AR model is so bad at estimating non-stationary data. Even so, let's have a look at how these predictions compare to the actual values over the same time period. Before we begin, make sure to once again set the end date back to January 1st, 2015. Okay, so we only need to add the testing set values to the graph. In fact, we only need to add the FTSE price between the start and end periods, since the rest is not relevant right now. We can also set the color of the new plot to blue to ensure it is distinctly different from the red we use for forecasting. After running the cell, we see a very interesting pattern. Over the course of the interval, actual prices cyclically jump up and down around the values we're expecting. So does this mean our choice of model is a good estimator for the long-run FTSE prices? Well, not really. If we zoom out again, we'll see how there is a trend where the values start to go up in a somewhat consistent fashion. However, our prediction curve continues to decrease. This shows once again that AR models aren't the best estimators of non-stationary data. Make sure you also change the title to something more appropriate, like Predictions versus Actual. For practice, you can check out what predictions the simple AR models make for the S&P and DAX prices. Try to decide whether the model is more accurate in the short or the long term. Now that we're familiar with the concept of forecasting and the predict method, we're ready to try out different models. Thanks for watching. Hello again. We already knew that AR models don't perform well when estimating non-stationary data, so it wasn't much of a surprise that the forecasts weren't extremely accurate either. Therefore, in this tutorial, we're going to switch to returns, since we already saw those are stationary. We'll also explore how some of the different types of models we've discussed perform when forecasting returns. Let's get coding. Lucky for us, we've created the returns for each series before splitting up the data, so we don't have to create them manually. Thus, we can start by defining and fitting the model. You've done this numerous times before, so just make sure you set the appropriate order and variable names. Next up, we need to actually make the predictions. For simplicity, you can reuse the code from the last lecture. What's left is to plot the predictions in the actual values, just like last time. After setting the appropriate names, we can also alter the title to make it clear we're using returns. And we're all set. After we plot the graph, we see what appears to be a constant line at the 0. This means that our model makes no predictions, since it assumes all future returns will be 0 or extremely close to it. This tells us that the coefficients for the past values, as well as the values themselves, must have low absolute values. If we quickly check out the summary table, we'll realize that the coefficients aren't even significant. Therefore, it makes sense for the model predictions to barely move over time. If we increase the order of the model to, say, 5, we'll see some very small shifts among the initial forecasts. However, the curve still flattens out very quickly, since forecasted values become smaller and smaller in absolute value. Additionally, we notice that for every single period where the values shift, they're moving in the opposite direction of where they should be going. In the first period, they should be going up, but they're decreasing. Then the opposite happens for the second forecast, and so on. Admittedly, increasing the order makes little difference in the forecasting capabilities of the model. Of course, we know AR models have their flaws, so let's see how some of the other models fare. Before we take a look at the MA model, make sure to set the end of the interval back to the benchmark date. Okay, the code we're going to use is the same, barring a few small changes to the variable names and the model order. You should know what each line of code does by now, so we can run the cell and move on to examining the results. We see a similar pattern, where the predictions are just a flat line very close to 0. To determine whether the values are 0, we can either zoom in, like the last time, or call the head method. For the sake of variety, let's use the latter. Immediately we spot that all the values after the first period don't change. But why is that? Is it because the error terms going forward don't exist? Is it because the MA coefficient is so small, we're essentially only left with a constant after the initial few time periods? For homework, you can determine this by trying out the MA models with higher lags. If predictions are equal to the constant after the qth prediction, then the reason is we no longer have error terms in the data. Okay, we just saw that the forecasting powers of the simple AR and MA models are low. So next time, we're going to combine the two and see if that makes a difference. Thanks for watching. Welcome back. In this lecture, we're going to continue examining different models and comparing how well they match real-world data. Last time we talked about the AR and MA models, so naturally we are continuing with the ARMA and the RMAX models. Let's get coding. By now you should feel comfortable defining and fitting a model, as well as predicting its values and plotting them on the screen. Thus, just like we did with the MA model, we'll skip over explaining each line of the code. Instead, we're going to jump straight into the results. We see a repetition of what we had for the simple AR and MA models, a very consistent line of predictions that looks constant from afar. If we examine the first 5 observations using the head method, we'll see that unlike the pure MA model, we're having values consistently decreasing, albeit very slowly. If we check out the last 5, we'll see that the curve even flattens out eventually. In short, we're seeing that the ARMA provides more reasonable predictions, as they don't just die off immediately. At the same time, the shifts are always in the same direction, down. This means that we'll still be having constantly decreasing returns, which isn't very realistic. On your own, you can try increasing the order a bit and comment on how that affects predictions. Do they seem more natural? Does the new curve shift up and down? Or is it consistently heading in either direction? How does our preferred ARMA model do? All right, you've had your time examining the ARMA forecasts, so let's move on to the RMAX model. In case you need a refresher, the RMAX is the non-integrated version of the REMAX. It is also an extension of the ARMA, which includes an exogenous variable or variables. In this case, we'll be using the returns of the other market indices as our exogenous variables. Once again, you should know what each line of code does by now. Nevertheless, there's one crucial difference from the ARMA model forecasts we just used, and we wish to draw your attention to it before running the code. Of course, we're talking about the exogenous variables. In particular, we want to discuss the variables we pass to the predict method. Unlike their counterparts we set when defining the model, the forecasting exogenous variables need to come from the testing set. This is because the entire predictions interval falls outside the training data set, DF. Additionally, we don't need to skip the first element of these time series. This is because we created returns before splitting the training and testing sets. That implies we'll have the returns value for every single time period of the testing set, which is fantastic. For the sake of consistency, we can always specify that we're passing the testing set values from the start to the end dates before running the cell. Okay, so we finally see that our predictions match the true values a lot more closely than ever before. In some instances, the model overshoots the predictions. In others, it underestimates the possible jumps. But overall, it follows the data really well. This indicates that including outside factors like other market value indexes improved the predictive power dramatically. But why is that so? A simple explanation is that regular ARMA models can't incorporate any outside real-world effects. By including other market indices, we're allowing the model to take into account data from today, as well as information from past periods. This is extremely useful because it makes estimations a lot more precise, as we can clearly see. However, there is a downside to max models. Although they can greatly improve the accuracy of our predictions, they can make forecasting impossible. But wait, didn't we say we're using forecasts and predictions interchangeably? Well, we did, up until now. In the beginning of this section, we mentioned how there is a very subtle difference between the two. The general agreement is that we use predictions when we're discussing in-sample estimations, and forecasts when we're talking about out-of-sample estimations. Basically, if we have a testing or validation set, we can get the values we need for the exogenous variables, so we make good predictions. However, we don't have those available for periods in the future, so we can end up making poor forecasts. In our case, we make fantastic predictions about FTSE returns using S&P, DAX, and Nikkei returns. However, we don't know what the values of each will be in the future, so we can't make accurate forecasts based on that. Now you see why max models can be great when we're analyzing data, but poor when we're trying to forecast it. Okay, implementing the ARIMA and ARIMAX is trivial at this point, since we only need to change the order in the methods we're using. To avoid spending more time on something you know or you can do on your own, implement these two models on your own and comment on the results. Just remember two important aspects. We only use integrated models on non-stationary data, so you should go back to using prices as your endogenous and exogenous variables. Additionally, predictions will be integrated prices. This is important because you will have to create a new series of integrated test prices to serve as the actual values. Okay, when we last discussed max models, we proceeded to add seasonal components to improve our estimations. In the next lecture, we're going to follow suit and explore the SARMA and SARMAX models. Thanks for watching. Hello there. In this tutorial, we're going to show you how to forecast time series data using seasonal models. We'll examine the SARMA and SARMAX and let you explore their integrated equivalents on your own. Without wasting any more time, let's start with the simpler of the two models, the SARMA. The code isn't much different from the ARMA one we explored in the last lecture, so we're only going to focus on the differences here. First and foremost, we're no longer calling the ARIMA method we've been using so far. Instead, we're switching to the SARIMAX. In case you need a refresher, we first came across this method and its peculiarities in the lecture on cyclical trends in time series. The main difference between seasonal and non-seasonal models is that the former also has seasonal orders. These are crucial and need to be specified when we define the model. As we've discussed before, the crucial argument is the length of the seasonal pattern, which is 5 in our case because a normal week consists of 5 business days. The rest of the orders can vary, as long as the non-seasonal ones are lower than S. That said, it's a good idea to break the mold and go for some higher lag orders. So we're only doing this for the sake of variety, so you can start with a simple SARMA model if you prefer. Lastly, make sure to change the names of all the necessary variables. Most importantly, please save the predictions into a new data frame, since we'll be comparing those later on. Now, let's have a look at the results. Once again, we see that most values are close to 0, as was the case for the ARMA model. However, this time the predictions curve is wiggly instead of being constantly decreasing. In other words, returns are going up and down instead of behaving identically throughout the interval. Despite this, the magnitude is far too small compared to the actual returns. This indicates that SARMA models anticipate greater stability than the MAX model we examined earlier. However, their accuracy is lacking. In fact, if we zoom in by changing the length of the interval, we'll see how our predictions are usually going in the opposite direction. Of course, there are some lucky overlaps where the values are extremely close after jumps and falls cancel each other out. However, these are rare and far in between, and we shouldn't be making our predictions solely based on these incidental matches. Now, before we move on to the SARMAX model, we have to revert the interval to its initial length. Great. As before, we're not writing out the entire code line by line since you already know what's happening here. The only important difference comes from defining the model. Since we have exogenous variables as well as seasonal orders, we need to specify both. With SARIMAX, we are basically combining the peculiarities of the max models and the seasonal models we just examined. As you can notice, the rest of the code is straightforward, and you should be able to replicate it easily. Have in mind that the more we complicate the model, the longer it will take to compute. Thus, this model might take a bit longer to compute than the rest. Once again, we can see a curve that follows the data very closely. A similar improvement occurred when we went from the ARMA to the RMAX, so adding exogenous variables drastically changes our predictions. Therefore, the best estimates seem to be ones where we're adding exogenous variables into the mix. To test if that's true, in the next lecture, we'll use the AutoArima to automatically select the best model and forecast its values. Thanks for watching. Hello again. Picking up where we left off, let's move on to forecasting with AutoArima. All the models until now relied on the ARIMA method from the Stats Models package, so we had to make minimal moving from one to the next. However, the AutoArima is part of the PMD ARIMA, which means we'll be using a new module with different methods. Of course, some similarities will persist, but make sure you understand all the differences. Okay, let's begin. We start by storing the results of the AutoArima. In the parenthesis, we need to pass the time series we're forecasting. We don't call the fit method because AutoArima returns a fitted model, and as expected, this will take some time. Okay, unlike the predict method from the Stats Models package, the one from the Pyramid ARIMA doesn't return a data frame, but an NP array. For anybody confused about what we're talking about, data frames and arrays are different objects in which we can store data that are both widely used for time series. We prefer using data frames because we can attach dates as indices. Doing so allows us to transform any sequence of data into a time series. Obviously, this is exactly what we plan on doing, so pay close attention. We set the data frame which will store our predictions and set it equal to pd.dataframe. This method will convert the data into our desired format. Inside the parenthesis, we call the predict method on the fitted model variable. Now, unlike the predict method from the Stats Models package, this one doesn't take start and end dates. Instead, we have an argument called n-periods, which indicates how many elements we're predicting. We set it equal to the length of the testing set, from the starting date to the ending date. This will ensure that we're making a prediction for every period of the testing set. Before we're done creating the time series, we also need to specify the date for each value, and we do so by setting the indices equal to the corresponding dates from the testing set. That's all there is to it. All we've got left to do is plot the graph. Here it is. We see that the predictions don't really match the curve as closely as the SARMAX model ones did in the last lecture. Of course, this is only the default best model, so we shouldn't be too bothered about its accuracy. In case you need a reminder of what we call a default best model, we suggest revisiting the section about the AutoArima. There are two obvious steps that are bound to result in a better fitting model. The first one is including the exogenous variables once again. If you decide to do so, be careful, because you need to pass the values to the exogenous argument rather than the exog we've been using so far. In addition, since we expect cyclical trends in the model, we can set the length of each season. Apart from that, we can loosen up the restrictions a bit by increasing the maximum allowed values of the seasonal and non-seasonal orders. By doing all of this, we're allowing the AutoArima method to explore even SARIMAX models, rather than be confined to just ARIMAs. Fantastic! Afterwards, we must create the new predictions data frame before producing its graph on the screen. Just make sure to set the same exogenous variables to the predict method, like the one you did when defining the model. Since the names are all the same, we can just call the cell where we plotted the predictions the first time around. What we get is a curve that matches the testing set far better. This just means that as long as we provide the AutoArima method with enough information, it's bound to give us a reasonable solution. All right. We notice how all the models that perform well rely on exogenous variables. However, those are hardly ever available when we want to make long-term predictions. We're reiterating this because our max models rely on outside data much more than they do on past values or past errors. In the next lecture, we're going to discuss some of the issues and pitfalls surrounding forecasting models and why certain types of models are better than others. Thanks for watching. Hello, everybody. Like everything else in data science, there must be a lecture about pitfalls or peculiarities. Some of these will be model-specific, others will be data-dependent, so you might have to account for several of them simultaneously. Okay, let's start with a very important reminder. Most of the models we examined in this section were non-integrated. Therefore, they automatically assumed the data is stationary. This is precisely why the forecasts for prices were worse than the forecasts for returns. If you recall, we compared the AICs of the best ARMA models for prices and returns, and the latter yielded a much lower result. So the first possible pitfall comes from picking an incorrect type of model, depending on the data. Of course, we can always forecast stationary returns and then create the prices based on these returns. Therefore, we can completely avoid working with non-stationary data. Before we begin talking about different types of models and how they underperform, let's spend a moment and plot all the models on the same graph. By looking at them simultaneously, we'll be able to comprehend just how well or poorly each model performs. We do so by plotting the predictions for each model in the same cell. The code isn't all too complex, so we'll just comment on several key aspects. The first one involves the figure size. We want a bigger plot because there will be many curves on the graph. Additionally, we want to know which curve is which, so we give out specific colors for each one. You can feel free to change these to your liking. We see that we already stored the predictions in separate data frames earlier, so we don't have to do any forecasting right now. Also, we're only including the values from the starting date to the ending date, even though all the data frames should already be that precise length. Using this syntax makes it easier if we want to examine a different interval. Finally, we're adding a legend to the plot, where we indicate which curve comes from each model without having to look at the code. Of course, we also set the title and call the PLT show method before running the cell. The blue line once again shows the true values, and the red line is the one that follows it best. That's the SARIMAX curve. But this really isn't all that surprising, right? Interestingly enough, we don't really see the curves for the AR or MA models. That's because Python layers the values on top of one another. Since the AR, MA, and ARMA basically flatten out, the ARMA line would appear on top because it was drawn last. Hence, the cyan curve is the one we see in the plot. Now that we have all the curves in front of our eyes, let's continue with the peculiarities. I'd like to spend a minute on integrated models, like the ARIMA. In this section, we left their implementation for homework, as it feels rather trivial at this point. The main issue here came from the lack of visualization. What we mean is that we can't plot the integrated predictions against the actual prices for the corresponding period. If you need a reminder, to work around this, we had to create time series of delta from the testing set in order to compare the integrated predictions with actual values. This is also why they don't appear on the screen right now, because we use them to model a different time series. Right. The next model that experienced issues when making predictions was the AR. It only depends on the past values and a coefficient, so we're getting a curve of constantly decreasing values. The more past lags we include, the more time it takes to flatten out. However, the monotonous nature of the predictions makes it unreasonable, since we don't really expect prices or returns to constantly be going down. Another type of model that experienced issues was the MA. The big issue here stems from the fact that we can't make long-run predictions if we're relying on error terms. That's due to the fact that we can't auto-generate future residuals since we don't have actual values anymore. Just in case you need a hint, the residual equals the true value minus the estimate. This is why any model which relies on error terms is not suitable for forecasting many periods ahead. One way to resolve this issue is to manually create white noise residual values for the entire time period we're forecasting. Then we can recursively create a time series of predictions based on the regression coefficients and the last few known residuals. The ARMA is just a combination of the AR and MA models. That's why it's prone to experiencing both types of errors we just noted. Of course, by creating the artificial MA residuals, we obviously get rid of the MA issue. However, since we're not dependent only on the AR components any longer, we're also solving the AR issue as well. Next up, we must once again mention the max models. If the exogenous variables are other time series as well, we'll run into some trouble. Here's the explanation. Not knowing how the exogenous variables shift make it impossible to predict how the endogenous would do that either. Since this sounds really difficult to accomplish, we can take a different approach. Right. We saw that most of the models we looked at experienced some issues. Some can be easily resolved, while others, not so much. This suggests that making accurate forecasts with the ARMA family of models isn't that easy. However, what if we didn't forecast the values themselves? Instead, we can focus on their volatility to determine the stability of certain markets. In the next lecture, we're going to use the ARCH and GARCH models to do precisely that. Thanks for watching. Hello again. In this lecture, we're going to discuss how to use the ARCH package to forecast volatility. So let's get coding right away, shall we? As always, we start by defining the model first. Unlike before, we'll need to pass the entire data frame as the endogenous variable rather than the training set. So make sure to use dfcomp. We'll be using a simple GARCH11 model. That means we don't have to specify any of the arguments right now, since those are the default. However, I'll still do it because it will enable us to try a different model by implementing minimal changes. Once we're done, it's time to fit the model. We set the last observation argument equal to the starting date of our predictions. This will ensure we're only fitting the training set into the model. Additionally, we set the update frequency to 10 to avoid many unnecessary outputs on the screen. Next up is the actual forecasting part. We create our new data frame and set it equal to the results variable and call the forecasting method. Two arguments are required. The first one is called horizon, and it determines how many observations we want our model to predict for each date. Since we're making predictions for each day, we can simply set it equal to 1. That way, for each date, we'll get the predicted value for the next date. The second argument is called align. It determines whether we match the value with the date the prediction is made on, or the one it's supposed to represent. Since we prefer the latter, we set it equal to target as opposed to origin. All we've got left to do is display the data. We'll do so by calling the plot method on the residual variance attribute of the data frame, storing our predictions. Of course, we're only interested in the values between the starting and the ending days, so we set those as our limits. We also add a title and the PLT show command, and we're done. We see a curve that fluctuates up and down and shows no obvious pattern. In other words, our volatility predictions aren't linear like the ARMA models, but fluctuate based on the past conditional variance. If we wish to get a bigger picture, we can delete end from our code. This will result in the plot method graphing all the values until the end of the data set. We actually see a lot more variation in the results than before, with several big spikes over the years. To get an idea of how well the model performs, we can compare it against the actual values. So let's add FTSE returns to the graph. Since volatility is always positive, we should opt for the absolute values instead. Also, make sure you set the appropriate Z order for each time series. Since we want the predictions to be displayed on top, we pass it the higher order, 2, and assign 1 to FTSE returns. Our model does a decent job predicting when shocks will happen, and does very well at determining periods of consecutive high and low volatility. It is usually a bit conservative during some transitional periods, but provides some good estimations nonetheless. Now, all of this is fantastic, but how is it different from the models we've observed so far? We're still only predicting values within the testing set rather than forecasting the future. Well, we can do that too. As we explained earlier, the horizon argument determines how many values we want to predict forward for each date. Currently, we have it set equal to 1 because we're only forecasting the value for tomorrow for each passing day. However, if we're forecasting, we don't need the one step ahead prediction for many days, but the exact opposite, the many step ahead prediction for a single day. To elaborate, if we set horizon to another value, like 100, we can forecast that exact number of days into the future. If we want to see what our forecasts would be, we're only interested in the 100 predictions made after the last day of our testing set. Thus, we can display the 100-day forecast by calling the residual variances and setting the starting date to -1. In case you need a reminder, that means we're starting from the last day of our data set. We see columns with names like H001, H002, and so on. The number following H states what day of our forecast we're on, with 1 being the first and 100 the last. Fantastic. We're finally able to forecast a model into the future. However, it's one that measures volatility rather than returns, and we can't transform those to get some price estimates. Before we started exploring volatility models, we mentioned that this is one of the ways we can go around the issue of missing exogenous variables. The other solution involves forecasting the values of each of these exogenous variables as well. We'll talk more about that in the next lecture. Thanks for watching. Hello there. In this lecture, we're going to discuss what a multivariate regression is, when we're interested in it, and what the easiest way to implement it in Python is. Now that we have our expectations set, let's begin with the definition. A multivariate regression is just several regressions in a trench coat. In other words, we have regressions stacked on top of one another, one for each time series we're including. For example, if we have a data set with 4 time series, a multivariate regression will fit a model for each one and include all of them in the regression. In terms of our data set, that would mean that we take S&P, FTSE, DAX, and Nikkei values, and we regress each one using all 4 to estimate values. Suppose we want to use an AR2 model. Then the multivariate regression would try to fit a model using the last 2 values of each time series. Thus, we'll have 4 regressions of the same model using different endogenous variables. Okay, so how do we tell these multivariate models apart from the ones we've been using so far? Well, these are called vector models because every component contains a value for each of the time series. If we wish to include past values, we'll be dealing with a vector autoregressive model, simply known as VAR. If we include past residuals in addition to that, we'll be dealing with a VARMA, and so on. Essentially, we can have multivariate vector equivalents for any of the models we've examined, all the way up to a vector Sarimax. Lucky for us, the stats models library in Python has the capabilities of implementing all these models. Right now, we'll see how to use a vector autoregressive model to make predictions, so let's get started. To begin with, we imported the VAR model from the Stats Models API. After that, we create a new time series data frame to serve as our endogenous variable. In our case, that will be a data frame containing the returns for all 4 market indices. We then create the model variable and name it accordingly. We set it equal to the var method and only pass the new endogenous variable as an argument. On the next line, we pass a value to the select order argument of our model. Whatever numeric value we pass will serve as the maximum order of the model. The more time series we are using, the higher this value should be, so we set it equal to 20. Next up, we need to fit the model. Before you do so, make sure you select AIC as the information criterion, since it's the one we used for all the AutoArima models. We can display the summary table to examine the results from fitting this model. You already know how to read these, so we'll only mention what is new here. For starters, we have 4 different summary tables, one for each time regression. The results for equation at the top indicate which series each summary table represents. As you can see, the first one says RET SPX, so it contains the values for the returns of the S&P 500. Next up, let's have a look at the coefficients. The first 4 after the constant start with L1, so they represent the AR coefficients for the first lag. The next 4 start with L2, so they're associated with the second lag, and so on. In total, we have 5 lags and 4 time series, or 20 coefficients in total. As you can see, having multiple endogenous variables drastically increases the order, which is why we decided to set the maximum to 20. Great. If we scroll to the bottom of the summary table, we'll see a correlation table. It indicates how correlated the different time series are. Of course, since the correlation of X and Y is the same as the correlation of Y and X, then this table would be diagonally symmetrical. Okay, now we're ready to showcase some predictions. As we've done throughout the section, we'll have a look at the entire code and dissect it line by line. First, let's create a variable that contains the lag order from the model. We use the KAR attribute of the results variable to extract it. We need to know this in order to provide the initial values necessary to make the first prediction. Next, we call the forecast method to make our predictions. Within the parenthesis, we define 2 things, the starting parameters and the length of our prediction interval. Since we want to slice up the data, we use the values command, which transforms the data frame into an NP array. This is just a useful coding trick we employ when we want to take advantage of certain properties of arrays. The negative lag order indicates we're using the last that many elements to make our first prediction. Of course, we apply the len method to determine how long our predictions interval should be. Just like with the AutoArima, these forecasts are returned as an array rather than a data frame. Hence, we create the time series using the PD data frame method. The data is obviously the new array we just generated, and the indexes will be the ones from the testing set. The only new aspect here is the name of the columns. We set them equal to the names of the columns of the testing set. However, since the first 4 of those are the ones for prices rather than returns, we specify that we want the ones from the 5th to 8th column. All right, the last part is the comparison, where we plot our predictions against the actual values for that interval. This should be trivial by now, so let's move on to the results. We see a predictions curve which flattens out after several periods. This is surprising because we're also including values for other variables, right? Well, not entirely. We're only including past values for these additional time series. Therefore, we're not including the extremely valuable input of today's values into the mix. This is why the model performs just like an expanded AR model. However, there is some value to it. The stats models module also includes a plot forecast method we haven't discussed. If we call this method on the results variable and pass a value like 1000 as its argument, we will get a plot with 1000 forecasts. In addition, we will also get an interval depicting the 2 standard deviations away from the forecast. That way, we get a 95% range for the returns of every market index moving forward. This will give us a great idea of whether we see long-term stability in the market, assuming no unpredictable event occurs. Fantastic! After seeing how to forecast various different models in Python, we're ready to fully and thoroughly analyze the time series. In the next section, we're going to go through the entire process of importing the data we want to analyze, pre-processing it in Python, finding the model that describes it best, and try to forecast it into the future. In particular, we're going to turn our attention to the automobile industry and examine Volkswagen's buyout of Porsche. See you all there, and thanks for watching.